sense, not the way in which we will be using it for most of this year. We'll be using something else. And more importantly, even this law, the way in which it's written, K, we'll dispense with K pretty quickly because K is actually a collection of other constants. So let's start with what I feel is an appropriate starting point, and that's a couple of one-dimensional questions. These will at least be more on par with what the expectation will be. Yesterday's hydrogen computation was to remind you that if we have to use real numbers, numbers that are actually reflected as the size of actual particles, then you need to be capable of using the scientific notation of your calculator and understand that your calculator can kind of get in the way. I'm going to assume that if you've made it this far, I don't have to teach you how to use your calculator. If that's not true, you should probably do some practice. Let's say I have two charges. Q1 and Q2. Yes, I'm using capital Qs because you need to be able to see the difference. You need to be able to see capital and lowercase. They change them all the time. And let's say they are separated by a distance r. And let's say that Q1 is 4 times the charge of Q2. Okay? Now, knowing that Q1 is 4 times Q2, we can do the whole problem in terms of Q2, and that'll be fine. But I'm just saying that we have one charge that is 4 times bigger than the other. Where can I place a third charge, Q3, so that when I release it, it won't go anywhere? That's not an answer to my question. You have Q1, Q2, Q3, and R. I think we can come up with an expression that tells us where we can place this charge. This is about the appropriate level for how to use Coulombs Law for a one-dimensional problem. And I want to kind of go through what it takes to solve this question. It's not as hard as it sounds, but it brings up 3 important details that I think you should highlight in your notes, numbered 1 through 3. Number 1, Coulombs Law only handles 2 charges at a time. Coulombs Law only handles 2 charges at a time. Point number 2, Coulombs Law determines the force on both charges. So although we compute a single value for F, it applies to each charge. Each charge is experiencing the same value of force. I'm not going to write all that out, but I'll say it again. Coulombs Law computes the value for both charges. Let's say Newton's third law consequence. So I'll just write third law here. And point 3, you mustn't forget that force is a vector quantity. You mustn't forget that force is a vector quantity. Now, let's start this problem out. Consider for just a moment Q3. Coulombs Law can only be conducted between any 2 charges at once, which means that these 2 constitute a pair of charges, and these 2 constitute a pair of charges, and these 2 constitute a pair of charges. Of these 3 possible combinations, which combinations are we going to have to look at? The yellow combination, the red combination, and or the green combination.
All three.
We will not have to look at all three. Yes, sir?
Red and green.
Not red and green. So we've kind of narrowed it down, haven't we? Yes, sir? Yellow and red. We'd like to know, and let me explain. The question was, where can I place Q3 so it experiences no force? In order to identify that, we are only interested in the forces on Q3. So the force between Q1 and Q2 doesn't matter. We're not interested in that force. But we are interested in the force between Q1 and Q3, and we're interested in the force between Q3 and Q2. Does that make sense? All right. We know that Q1 is equal to 4 times Q2. So Q1 and Q2 must be of the same type of charge. They're either both positive or both negative. If you're going to want that to be me recognizing that your hand is up, you're going to have to do a better job. Yes, sir.
If they're the same charge, then, well, I mean, either way, wouldn't Q1 and Q2 have an effect on each other? Like,
Oh, most certainly, but we're not interested in the effect on them. That's not what the question asked.
but wouldn't their distance also affect the answer for Q3's distance? Because if they're pushing each other or pulling each other, it would change where Q3 has to be.
So you want me to say something like Q1 and Q2 are fixed in place? Does that satisfy your problem?
Yeah.
Okay. To satisfy his question, Q1 and Q3 are fixed in place, glued down to ensure they don't move.
And also, we assume that Q3, wait, does it matter what charge Q3 is?
Well, if I could talk a little further, it might. I haven't gotten that far. I was attempting to.
Or
Keep going? You sure?
Well, I mean, in my head, I would think it doesn't, because if they're pulling, they'd both be pulling, and if they're pushing, they'd both be pushing. So, like, I feel like it wouldn't make a difference.
Well, if Q3 is negative and the other two are positive, then it would attract both.
depending on how strong the force is.
I think we should all just let them say.
Guys, there's nothing wrong with this conversation. Let's identify some possibilities, shall we? It doesn't matter to me. Let's pick somebody. Marco, is Q1 in this instance, is Q2 positive or negative? Just choose. Flip a coin. All right. If Q2 is positive, Q1 is 4 times Q2. That makes Q1 positive. Now, we'll try other alternatives. I'm just saying this right now, okay? Now, we could make them both negative, but Marco picked positive. So just chill your boots for a minute. Now, let's consider what happens if Q3 is positive. Let's start by pairing up Q1 and Q3. Are they of like charge or unlike charge? Will that be a force of repulsion or a force of attraction?
Repulsion.
So that suggests a force this way on charge 3 from charge 1. Good so far? Because there's also a force this way on charge 1 from charge 3. But that's what repulsion looks like. Are we sure we're good here? I'm not trying to make it hard. Like charges repel. All right, let's pair up Q3 and Q2. Are they of like charge or unlike charge?
Like charge.
Excellent. Will that be a force of attraction or a force of repulsion?
Repulsion.
Excellent. So under that circumstance, that would be a force this way on Q3 and this way on Q2. Now, I'm only interested in Q3, but can we agree that there's a possibility that if I choose the right location, those two forces could balance? If those two forces balance, would that suggest the charge won't go nowhere? All right, so apparently, if it's a positive charge, this all works out. But we weren't told. So let's consider the possibility that Q3 could be negative. All right, Q3 is negative. Let's pair up Q1 and Q3. Are they a like charge or unlike charge? Is that going to be a force of attraction or a force of repulsion? So, good for you. I know I'm being ridiculously slow and methodical, but I don't want to see this again in a few minutes, so I want to be slow and methodical. Q3 and Q2 now. Like charge or unlike charge? Attraction or repulsion? Is it possible that those two could be in balance? Yes. Now, I'll ask again, does it matter if we know or don't know Q3's charge? Like, does it matter if it's positive? Does it matter if it's negative? No. Doesn't appear to be. Now, as just a supposition, do I have to go through this over again if Q1 and Q2 are both negative? Do you recognize we're going to have the same set of arguments, same set of circumstances? However, it's a no-go now, right? Doesn't matter whether Q3 is positive or negative. Do you understand that there will be no place between the two particles where the net force could be 0 on Q3 if one was positive and one was negative? If you don't believe me, you need to do that on your own. However, be aware, that doesn't mean there couldn't be a place out here where the net force could be 0. You should look into that. You really should. I'm not going to right now. I'm trying to be slow and methodical. Any slower, and Mr. Shelton's head will explode. So, start here. Good place to begin. All right, so for the next few moments, I'm no longer going to refer to Q1 as Q1. I was doing that so I could have a way to refer to it. I'm going to refer to it from now on as 4 times Q2. And I'm going to consider this pairing first and this pairing second. Okay? So, let's start with Coulombs Law for the leftmost charge and Q3. Now that's going to be 4 Q2 times Q3 times K over... that's going to be a problem. That distance. I don't know what that distance is. We're looking for this distance. So I'm going to pick something. I'm just going to call this distance, for lack of better terms, X. X will not be allowed to be in my answer. I'm making it up, and therefore it was not given to me. But I believe we actually want the solution to what X equals as our answer. But I'm going to put X squared. That's got to be the force on Q3 from the 4Q2. All right, let's do the next force. This is the force on Q3 from the rightmost charge. And you shouldn't need me to do this. You should be able to do this without my assistance. Let's assume that you can. Take a moment, write that out. I'll give a hint that the distance between Q3 and the rightmost charge could be written as R minus X. That's what this distance would be. I don't want to introduce another variable, but since R can be in my answer, I would like to introduce R somehow. So this distance has to be R minus X. How we doing?
I ask a quick question?
I know you will.
May I?
Just do it, please.
Sorry. So
This isn't AP1 anymore. Just, speak your mind.
Word.
If it's related to physics and what I'm talking about in class.
So does R dignify?
Dignify, I don't think that's the word you want to use here.
Does R represent Q3's like distance from Q or Q2?
No. R represents the separation distance between the leftmost charge and the rightmost charge. It was given in the problem. Two charges separated by a distance R.
Okay.
Okay?
Why is R not on the other?
That's the
equation?
They'll,
Oh, okay. I saw it. I visualized it.
okay. Yes, sir?
So, first of all, can R hat be negative?
R hat is a unit vector, has a value of 1, and can't be negative, but I don't think that's, I'm not sure that's not an appropriate question. R hat carries with it direction information only. So ideally, yes, it could be negative, but it could also be up, right, or east.
So how do you know what direction it's going?
So this problem was about several things. It was about trying to figure out and ascertain if there is a reasonable location between the two particles where the net force could be 0. How does the value of the charge, positive or negative, affect whether that position is stable for both positive and negative charges? And is there a way that we could determine where this location happens to be? Now, we haven't gotten all the way there yet, but we do now have an expression for the force on Q3 from the leftmost charge, that's this one, using Coulombs Law, and the force on Q3 from the rightmost charge, that's this one. If we want to find the place where this charge, when released, will not be pushed off of this location, then we need the two forces to be equal. If they are equal, then the net force on the particle will be 0. I know for you guys who haven't had a course in physics that might be tough, but I believe that you can probably figure that out. If you push equally on something in two opposite directions, it won't go anywhere. Kind of like your butt pushing on the chair and the chair pushing on your butt. Butt staying in place. Not so that's gravity on your butt, the chair on your butt, but. Now, I hope you see something important here. You may not see it, but all that long conversation about whether Q3 was positive or negative and how that would matter didn't ever matter. Mathematically, Q3 does not contribute to this answer. So not only does the type of charge not matter, but the size of that charge also doesn't matter. In fact, Q3 doesn't even play a role in the answer. The only thing that determines where this location is the value of Q1 and Q2. And even that plays less of a role than it looks. Because Q1 is 4 times Q2, it's the proportion that mattered. Now, if I told you that one of them was 1 coulomb and one of them was 12 coulombs, well, you could probably put that in too. Or 5 electrons and 5 plus 1 electrons. I don't know. Notice K doesn't matter either. Leaving us with 4 r minus x squared equals x squared. Now, suddenly, this problem has become a lot less interesting to me. I don't feel compelled to solve it because all the physics is gone and now it's just solving for x. You could take the square root of both sides to do so. I would caution you not to do that. If you take the square root of both sides to do so, you need to remember that it's plus or minus the square root, which produces 4 possible solutions if you do it that way, because you have to have plus or minus the left side and plus or minus the right side. So perhaps don't do that. Perhaps expand and solve for x. That will be better for you. So I know you guys like having answers, but you do understand now we've exhausted the physics. Right now we're just solving for x. So 4 times r squared minus 2rx plus x squared equals x squared. Standard expansion. Distribute the 4. And now here's where we reach one of those points where you might have difficulty. Do you know how to solve this from here? I don't know that you do, but I'm just curious. This might be one of those things where you don't know how to do the next portion. I would always test to see if it factors. But I don't know if there's any way to set this one up so that it does factor. It might. Separating the 4 into 2 gives me 2 times 3 is 6, and another 2. That could add up to be 8. So I would try that first and see if it works. Factoring is always best. If you can't, then you've got to do quadratic formula with a variable. It's not terrible, but we should try and see if we can factor it first. So I'm going to look for factors and see if there's possible factors. For example, I'll move that up there if you guys are trying to see. I could put 3x and x here. I could put 2r and 2r here. I need this to be positive so that either they're both negative or they're both positive. This one's negative, so I'm going to try out both negative. Two times 3 is 6, plus 2 is 8. I think that set of factors works. You guys okay with it? So I have 2 possible answers. I have x equals 2/3 r as one answer, and x equals 2r as the other answer. I bet there's only one place where this is actually true. I'm getting 2 answers, but I don't think there really is 2 answers. Why is one of these answers probably not true? Yes, sir?
Because if it's outside of the pair of particles, both forces would be attractive. Towards the set of particles.
That's right. So let's handle what's happening here. If we bring back our number line, and note that we have a charge here and a charge here, and they're separated by r. Assuming they're all positive, just to make it easy, because we know it doesn't matter if Q3 is positive or negative, it's clear that in between, it's going to experience opposing forces. But if they're both positive, and I place the particle over here and it's positive, well then, won't these 2 cause a force in this direction, and these 2 cause a force in that direction? Is there any chance it would sit still over there? No. This is not a reasonable answer. So we have to throw that one out. This one, very reasonable. It's 2/3 r away from the larger charge, which is Q1. Now, this location is actually a stable equilibrium. If you consider what would happen if you move that particle to the side a little bit, the force on the particle would be to push it back towards this equilibrium point. So this point is kind of a stable equilibrium. We'll be looking at these kinds of situations in which an equilibrium is stable. But this represents one kind of stable equilibrium. There will be unstable equilibriums in the future too. All right. Whee! How how about something else? This one's one-dimensional. And of one-dimensional problems like this, there's a variety of alternatives that are similar. You as well. There's this problem where you're looking for a point where the net force is equal to 0. There is the same style of problem when Q1 and Q2 are of opposite charge, and you're looking for this equilibrium position outside the two particles. So you should expect both kinds of problems. They're not particularly interesting in that once you've done one of these, they're all about the same. So if I said that this one was negative 4 Q2, then there's probably a place maybe out here or out here where there's a similar equilibrium position. Yes, ma'am.
So when you have the two answers, one obviously is outside in between and one is on the inside. So if they're the same charge and it's on the inside, and if they're opposite, it's on the outside, right?
No.
No? Okay.
I'm not sure your question was specific enough for me to answer it. Q1 and Q3 are the same charge. The only place are the same type of charge.
Okay.
Both positive or both negative. The only place there could be an equilibrium position is in between them.
Okay. Yeah, how do I tell whether or not it's going to be on the inside or on the outside?
Test it.
That's it.
So, consider doing what we did. So let's say I have, this one's positive, this one's negative. Test. Is there a place that you can put a positive charge in between where they could possibly have opposing forces? You're shrugging your shoulders, but is there any place in between here? And if I move over here a little bit, is that going to make the direction of the forces on that particle change direction? If I move it over here a little bit, will that make the forces on that particle change direction? It'll change the size of those forces, sure, but will it change the direction of those forces? No. So there's no place in between those particles that, where I'm going to have suddenly the two forces pointed in the same direction. Now, if I come out here, well, now I've got the different possibility, right? This one, there's an attractive force between these two, and there's a repulsive force between those two. I have opposing forces here. Anywhere I am out here, I'm going to have opposing forces. They're not going to change direction, but there's the possibility of it having equilibrium out there. Same thing over here. There's the possibility of it having equilibrium out there. I don't know which one would be right. It probably depends on how big this charge is compared to this charge. Let's face it, if it's a smaller charge, you've got to get closer to it in order to get more force. So probably it's going to be outside of the smaller charge, not outside of the bigger charge. Okay? You might have to do that kind of reasoning.
No, scared, man.
All right. I have a square with 3 charges placed at 3 corners. Let's call this Q, 3Q, and negative 2Q. I bring a 4th charge and place it here. And let's say, for argument's purposes here, it has charge positive Q. I would like to find the size and the direction. It's important, size and direction of the force on the blue charge. Let's assume it's a square of side length s. Now, you guys are going to leave tonight, but I have a bit of homework for you. And please don't disappoint me. Come tomorrow with this portion prepared. I see 3 pairs of charges that influence the blue charge. This one, and this one. Do you see those 3 pairs?
Yes.
Please come to school with the magnitude of the force for each pair. Just Coulombs Law for each pair. Answer this question. So I want to blow through this now because I need to give you some terms I want you to understand. First, your book, if you read the book on this, they have a way of writing the forces that has to do with numbering the charges. For example, the force that I've drawn with this green arrow would be the force on charge 4 from charge 3. Or if you open up the book I just read, it'd be the force on charge 4 from charge 3, and you write it like this. The force from 3 on 4, or the force on 4 from 3. There's no agreement in textbooks about the way you should write this. So your textbook and the book I was reading, they're different, and no one has a way. I don't usually do this, but I wanted you to at least see this in case you start reading your textbook. Because there's also a force this direction. Would you agree? And the force this direction I would write as force from charge 1 on charge 4. Now at the same time, there's a force this way. And this would be the force from charge 4 on charge 3. And there's a force this way. And this is a force from charge 4 on charge 1. God, I can't say it. So if you really want to get technical, you could devise a complicated way of keeping track of each of the forces by number. I tend to not do that, but your book does it. So to me, because we're having a conversation, can be a little bit more colloquial. And we can just, I can write them in terms of colors if you'd like. It really depends on you guys. You guys all claim to be visual learners. You'd say I should color code all of it. Visual learners really just means you want me to show you how to do it as opposed to you figuring it out on your own. So let's be really clear. Visual learning. Let's translate that. Lazy. You do it, Mr. Sheldon. I'll watch. So I'm not going to use this. It's just it just gets in the way, in my opinion. I'm going to use a color coding for the problems usually. And I'm going to say this is the force that exists between charge 3 and charge 4. And then there is a force that exists between charge 1 and charge 4. Those two are pretty easy to do and pretty easy for us to write out. So if I was to write them out based on what's sitting here right now, can we agree that the green one is going to be, looks like Q times K over S squared? That would be the size of that force. Any problem with that? And then the red one would be 2Q times K over S squared. Oh, these are just magnitudes. I haven't started talking about direction yet. So we're okay with all that? So now there's also a force this way. Now, I think there's a certain amount of symmetry here that we can use to our advantage. And I hope you see that kind of symmetry. That, like, this has got to be 45 degrees. Can we all agree that that's got to be the symmetry there? The real question is, did you figure out this distance? I would just write down square root of 2 times s. But you guys might have to figure it out. which would be like what, s squared plus s squared equals whatever this diagonal is squared. I can go the whole route, but this has to be the square root of s squared plus s squared, which just ends up being the root of 2 times s. We okay with that? So I'm good to move on? Oh, good. So I can't squeeze that in down there, so I'm just going to write F equals 3q times q times k over square root of 2s squared. We good? All right. Now, getting this answer's going to be a little more work. But right now, you should have gotten last night the 3 individual components of the force that will contribute to the net force on that particle. So, am I good to move on from here? Because, to be honest, kind of done with Coulombs Law. Coulombs Law is just charge times k divided by separation distance squared. That's Coulombs Law. All we're doing is applying it. In this problem is more about geometry than it is about Coulombs Law. Because this was the easy part of the problem. But it was also the part that has to do with what we've been taught so far this year. What I'm about to do next is something you were supposed to bring into the room with you when you came to this class. Because what I would really like to have is what is the actual net force on the particle? The value. Maybe even the value and the direction. A harder question, to be sure. So can we move on with this? If you were in my class last year, you know that one way to add vectors together is just list them out in terms of their x direction and y direction, and you add components together. There really isn't many alternatives to doing this. There are a few, but not many. For example, the green force is 100% in the y direction, and based on what I've drawn for x and y, it's negative. So I'd say the green one is 0x hat minus q squared k over s squared y hat. I've taken the force and now written it as a vector equation, identifying how much of it is acting in the x direction and how much is acting in the y direction. Are we okay so far? I'm trying to hit your prior knowledge. Am I doing so? If you don't know how to do this or you don't know what I'm doing, please don't wait until tomorrow. Stop now and say, I don't understand. Because if that's true, no hands went up, you should already be done with F. Because I'm boring you and you already went ahead. Still okay?
So is this where direction comes into play? Or do you
Yeah.
line it up?
Yeah. So the yellow one. Luckily, the yellow one has a certain amount of symmetry we can use here. So stop me if I'm jumping ahead too far. But I see 3q squared k over square root of 2s squared times the, let's go with sine. I'll go with cosine of 45 because I know that's what you would have used in your pre-calc class for the x direction. And then type x hat. Minus 3q squared k over square root of 2s squared sine 45 y hat direction. If only Evan was here to see all the letters now. We good so far? Are we sure? Want to make sure everybody's good. Because symmetry is important. We should exploit it as much as possible. So I'm not going to use cosine and sine of 45 because you guys already have an expression for those two, right? Square root of 2 over 2? Or 1 over square root of 2? Pick one. But we'll do that kind of stuff a lot. So the fact that it's 45 means I'm not going to leave that here. And I'm not going to use a decimal. I'm going to use square root of 2 over 2. You have to rewrite it. And rewrite it in your notes. Don't erase and put this in here. Just rewrite it real quick. That way you know the train of thought I'm using. I'm telling you this because it's a square. Because it's a square, the diagonal was going to produce a square root of 2. And the sine and cosine both are also producing a square root of 2. So often you're going to get these 2's in here that may or may not cancel out, but are likely to cancel out later. So try and remember, if you're using a square, the diagonal and the sines and cosines, which will do your components, are going to be related together. This is a mess, isn't it? Just a mess. But do you notice that every single term is q squared k over s squared? Every term. You could factor that out. There's absolutely no reason to keep it like that. Meaning, this could be written as just 0x hat minus y hat times q squared k over s squared. Just pull that part out. This one, negative 2x hat minus 0y hat q squared k over s squared. Let's get those out. They're just in the way. They're distracting from the part that matters. Get all that out of there. And I'm going to have a 2s squared on the bottom times 2 gives me 4 on the bottom. And a 3 times the root of 2 on the top. I'm just looking at the number part that was left. Are we okay with that? Or should I go slower? Yes, sir.
Other questions a little bit before that, but on the yellow force, you put the y vector as negative. Like, can you explain why that one's negative and the x one's positive?
That should be positive.
Should the x one be negative?
In the yellow one?
Yeah.
No, because it goes to the right, and the right was the positive direction. When I look at this picture, right, the yellow one's going this way and this way. So the x portion is positive and the y portion is negative. Is that okay?
Yeah.
I did gloss over that. Sorry. I shouldn't have. All right. God, we're nearing the end. I'm pretty sure the other component is going to be exactly the same, but negative, right? So minus 3 root of 2 over 4 y hat. Wow, what a mess. It's going to get messier. And you're wondering, Mr. Sheldon, do I have to do this on a test? Very unlikely. It's been on the FRQs before, but there was enough symmetry where all the components were the same. But I'll show you what this looks like when it's on the exam. At this point, you just add down the columns, right? But we have a square root of 2 in there. I would hold on to the square root of 2 for a minute. But the left column will be negative 2 plus 3 root of 2 over 4 x hat minus, let me put a plus, and then I'll put minus 1 minus 3 root of 2 over 4 y hat. And all of that is times q squared k over s squared. What a mess. Now, this is the answer. This is the size of the force on that particle. Technically, you could leave it here. However, if they asked you for the magnitude of the force, you would probably have to keep going. So let's pause here so that you guys can do something in your notes that I think is useful. Okay? For all of you who are wondering, oh my God, I can never do this. Was it hard to figure out the individual forces themselves? No. Was it hard to take each force and place it in an x hat or y hat direction? These parts aren't hard. The end is a mess, but individually, they're not hard. We did 3 things today because we went on a tangent. We found the individual sizes of each force. That part, the hardest part was finding the diagonal. We broke them up into components. And then we added the components together. That's all we did, and it took us 28 minutes to do so.
Word.
The most straightforward question here would be to ask, what is the force on one of the charged particles? Can we agree that the force will be the same on all 3 charged particles because of the symmetry in the system? So that's not the exploitable symmetry that I want to talk about, but it is a very symmetric problem. So in order to make this problem, I think, reasonable for us, but also a little bit simpler, I'm going to focus on this charge and the force on this charge. But can we assume that whatever force we find for that charge will be same for all 3 and will be directed away from the center of the triangle through the vertice? Do you understand that phrasing? Does that have enough vocabulary in it for you that you recognize? Or do you want me to say it differently? I can, I just don't want to. So I think if we, don't want to do that. If we consider that this line is a line drawn through the center of this triangle that bisects the other side, the force acting on that charge would probably be in this direction. Does that make sense? And we could do that for each of these charges. That for each of these charges, we can kind of imagine this line that bisects the triangle and is directed. I know. And is directed away from the center of the triangle. And that would be the direction of the force. So, do you see why I want to pick the top charge to work from? So we're going to pick that charge. Get rid of all these other lines. I think now would be an excellent time to mow the lawn. We're not doing anything in here. So I want to put this line in place because we're going to need to do a little work here, and I want that line to be clear to all of us. This line is perfectly vertical. So it represents, in my mind, the vertical axes of a coordinate system that is centered on this charge. I'm going to tone the color of the line down a little bit, just so it's not so prominent. There, I think that's a little bit toned down. There's also, I think you could agree, a horizontal axis that would accompany this. So I'm kind of putting these axes in here to give us a point of reference so that we can kind of determine not only the size of the force acting on the charge, but the direction. If you need to label it, then, by all means, this is the X direction, this is the Y direction. when I look at this, I'm going to remind you that the Coulombs force is a force between two particles at a time. So I see the possibility of three pairs of particles that represent pairs of forces. There's this pair, and this pair. A, B, and C. Do I have to consider all three pairs of particles?
No.
No. Which pairs do I have to consider?
A and B.
A and B. So A and B are the only two pairs of particles that are contributing to the force on the top charge. Everybody okay with that? So let's consider this pair first. Can we agree that there will be a force directed along the line that connects those two charges? And that them being the same charge, that will be a repulsive force, and that force will be directed, I guess, upwards and to the right. Now, that's not all. We know more. If this is an equilateral triangle, as I stated yesterday, then we know this is 30 degrees. Right, it's an equilateral triangle. Any question about that? Now, let's say instead of an equilateral triangle, it was isosceles. I'm bringing this up because that would be the first thing I would change about this problem if I was to give it to you for homework. If it were isosceles, I wouldn't necessarily know that this was 30 degrees. I might be just forced to label it theta. And I could probably come up with some way of determining what the size of that angle is. For example, I would know that there's this side length and perhaps something I could use for this side length. I might be able to determine something about that angle from the other portions of the geometry. And if you don't know why I'm saying this, you haven't looked at the homework yet. How many of you have looked at the homework? So when we're done with this, I'm going to show you an example, and you'll understand why I'm bringing up this conversation, okay? So for this problem, we know it's an equilateral triangle, so that makes that 30 degrees. We can leave that 30 degrees in there. Just be aware, you need to be looking at your geometry closely. Now, I'm going to throw out there that this part isn't hardly any work, right? Although Coulombs Law is the name of the chapter, Coulombs Law is the easiest part of all of this. Do you agree that with the coordinate system we have placed here in the problem, there are two components to the force acting on that charge? That although we show it being drawn upwards and to the right, based on your knowledge of pre-calculus, and for the most part, those of you who have had physics before, you realize there is a component of the force that is aligned with the y direction, and a component of the force that is aligned with the x direction. We're likely going to have to use those pretty often, like we did yesterday, where we had the three forces and we had to find out how much of each force was in the x and y direction when we were going to go further and add those components up. So I'm doing the same thing here. I'm suggesting that the vector description of this force will have a portion of the force in the x direction and a portion of that force in the y direction. And that looking at this picture, I could probably do a little bit of trig and recognize that the x direction is going to be based on sine of 30 degrees. Right, that's this portion, that is the opposite side. So I kind of see the sine of 30 there. And this side based on the cosine of 30 degrees. I'm doing this purposefully because it goes against what you guys learn in pre-calc. I want to make sure that we handle each triangle as given to us, not try to impress upon it that x always goes with cosine and y always goes with sine. If you do that in this class, you're going to fail terribly. So approach each triangle, look for the side that's the opposite, look for the side that's the adjacent, and recognize that in this case, this will be f sine 30. This will be f cosine 30, where f is all of that. How are we doing? Not terrible? All right. Exploitable symmetry. We have some symmetry we can exploit here. The fact that all the charges are the same tells me that there's going to be a similar size force on this side. That has to be true, because the two charges are the same and the distance away is the same. But because this is a equilateral triangle, that also suggests that the direction of this force will also be directed at an angle of 30 degrees. Now, just a quick look at this suggests that the off-axis components of force are going to cancel out. I'll use that phrase a lot in here, and you may wish to kind of put a box somewhere. Off-axis components. This happens a lot. And this is what I mean by symmetry. The two charges at the base are in such a position as to produce forces that have the same angle but in two opposite directions. What I mean is, there is clearly a component of the force that is to the left. And based on the symmetry, this component of force and this component of force are the same. Because of that, I can tell without doing any work that those two are likely to cancel out. And because they're likely to cancel out, I don't even have to consider them in the execution of this problem. I can clearly see that by symmetry, the x components will sum to 0. Now, you don't have to believe me, but if I do the whole work to consider what the vector components are going to be, the only difference between this and what I'm going to write out over here is that one of them is going to have a negative in front of the x component and the other one's not. If you can see the symmetry before you start the problem, then you can probably save yourself quite a bit of time and not even bother to worry about any of the off-axis components that you know will cancel out. And recognize that the only component you need is the one that is directed along the axis, in this case, the y-axis. So how many contributions to the y-axis component are there going to be? 2. So I care about this. Take whatever that is, multiply it by 2, because that's the only 2 that are going to contribute to the force. The other 2 components cancel out. So all right?
Yep.
Now, I spoke around this problem a lot, but do you notice that you probably don't have to spend nearly as much time? Once you realize that there's a certain amount of symmetry, this goes pretty quick. So let me pause here, find my coffee, and entertain any questions you might have. Okay, so I have 2. Kyle?
it's just in the future, are we gonna go through problems where it's like a 3D, where we have like X, Y, and then going from like a maybe, like I said, just going here, there's also one coming down.
There are very few three-dimensional electrostatic problems that don't also have one-dimensional symmetry.
Okay.
So this problem has one-dimensional symmetry. The force is directed along a single y-axis, right? The second dimension cancels out. We will have three-dimensional problems whose force will be directed along one dimension.
Okay.
And I'll show you an example of that as soon as we're done with this example. Yes, ma'am?
If the particle on the top is, like, the charges are both repulsive on it, what's keeping it in place? since
Okay,
it's
so,
going in the opposite direction?
I've gotten this question from 3 of you about the electrostatic problems, and so I'm gonna answer this as best as I can. Electrostatic problems are exactly that. They are static problems. We are making the assumption that the particles themselves are not moving at the moment we're observing them. Now, let's say that this is a real thing, and I attempt to place 3 charged particles here. Well, unless I can instantaneously place them and release them, I would probably have to have something here to hold them in place while I do this. Right? In a real world, if I put the first particle here, that one's fine because there's nothing else in space that's going to push on it. But the moment I bring the second particle here, these two will experience a force and they'll push each other apart before I ever get the third particle in place. The assumption is, we assume that these particles are there in space for this instant in time. And for that instant, we are looking for the force on them. If that force is effective at moving the particles, they don't stay arranged like this for very long. Does that answer your question? So, and let me also be very clear. These are not real things that we could actually create in space. These are contrived problems for the purpose of detailing how this one portion of electrostatics operates. You really could not create this in space. We could not isolate particles this well and have them sit in space so patiently for us while we attempt to make these calculations. So these are really problems that are training you as to how Coulombs Law works and how to deal with the geometry of the question. You guys follow along so far? Now, for just a moment, let me ask tends to look like on how this problem and this problem are really the same. By giving you a equilateral triangle, I gave you the answer. Right? I gave you 30 degrees. P exam. If you've looked at your homework, you've seen that this is one of your questions. This is a super common question. And there's a lot here to unpack, but can you see what's happening here in this problem? I have 2 charged particles that are equidistant from each other. And this point here in the center, we just call this the origin. I have a third particle that's located and directed along an axis that is directed down the center of the 2 charges. So this blue line bisects the other blue line. Good so far? Do you see how this is the same problem that you just did? Except that it's an isosceles triangle and not a equilateral triangle. So if I asked for the force on this particle, you really wouldn't have too much work to do. Except, what did I not give you?
The angle.
And the angle is the first thing I did not give you. And what else did I not give you?
How long distance between particles?
I did not give you the distance between the particles. Did I give you a method to find the distance between the particles? I think so. I don't know that everybody else sees it that way. But to me, your teacher, I'm giving you the same problem I just gave you. To you, that's probably not true. Especially if what I say is, I would like you to tell me what the force on the particle is using only the terms that are written down and any fundamental constant. If you don't understand the language of what I just said, you can't have theta in your answer. There is no theta. It's not written here. So since this is your homework, I think it might be appropriate for me to give you some pointers as to how to do this problem. But why don't you draw it out first? Something that you might be able to slap a ruler next to, or maybe a helper thing, so you can kind of get a feel for how this problem will look. And this will be the end of what we're going to talk about. Raise your hand if you see the exploitable symmetry here. That's good, because I have exploitable symmetry. If I call the vertical axis the y direction and I call the horizontal axis the x direction, then I think we can all identify this as our x direction. That good? And if I just for the moment consider this pair of particles, then I can imagine that there is a line that connects the two pairs of particles. That's the line I've drawn that connects the two pair of particles. I also then think that there is a force in this direction. And I see that force as being Q1, Q2, K over R squared. And it's directed in that angle. Now, I can't use R in my answer. And more importantly, in my head, I think there's another force in this direction that is of equal size but directed below the axis. Can you imagine that one too? Because that's going to come from the force between these two particles. I'm saying that because I think if I'm really careful, I only have to worry about the x component of both of those forces, and I can ignore the y component of both of those forces. You guys okay with that so far? So I really want the x component, which is going to be based on apparently the cosine of that angle. I know I can't have theta in my answer, but I have to imagine there's an angle there, right? And that's the only way I know to deal with the trig, and that means and in addition to this, I know there are two contributions to that force. Now, I'm kind of hoping you guys are following this line of reasoning. Now, I'm not writing all these things down, and I'm saying if you want to be able to do your homework, you might want to write down some of the things we're talking about here. And understand, I'm still telling you, only these things can be in your answer. So I've added stuff to this problem that can't be in my answer. So how do you proceed? I'll give you a hint. Super simple hint. R has to equal the square root of z squared plus a squared. Right, don't you see that right triangle that's there? Do you see it? Can we all agree that that has to be the length of r? Because we know the Pythagorean theorem. I used to just assume everybody saw that because I saw it. But I don't make that assumption anymore. The triangle I'm talking about is like right here. There's a right angle there. Now that part's easy, I think. I think that's not so terrible. The next thing, I think, takes a logical leap. We've already made several logical leaps here today. We've talked about off-axis components canceling out, using exploitable symmetry, and now we're having to exploit the geometry. So our problems, we hope, will have not only exploitable symmetry, but exploitable geometry. And I think there's something here we can exploit, some exploitable geometry. And I don't know if you see it like the same way I see it. But I remember my freshman geometry. Actually, I took it in the 8th grade. When did you guys take geometry? All right, so if that's true, then you remember the phrase, vertical angles are congruent. This angle and this angle represent a vertical angle. Any time a pair of lines crosses, it creates two pairs of vertical angles. That's two crossing lines. Therefore, this must be theta. Well, if that's theta, the cosine of theta would have to be the adjacent side divided by the hypotenuse. I'm exploiting the geometry in order to place my answer in the terms I'm allowed to use. I'm not allowed to use theta in my answer. I am allowed to use A and Z in my answer. So I could probably write this as Z over the square root of Z squared plus A squared. I'm exploiting the geometry and I'm exploiting the symmetry all at the same time. Now, pause, time out. You do here, all I had to do is make an isosceles triangle and you lost that. But really, you still have it, right? You have enough information. It's just that your answer is going to look a little bit more, what's the word? Freaky. You ready? Let's put it all together. Because we have something to use for cosine, we have something to use for r, and we have the answer right there. All we got to do is mash it all together, and we have the answer to this question. Oh, I was hoping the answer would be a number. Never. So I'll make that a little bit smaller because, I want to make this nice and pretty. F equals 2q1 Q2K over R squared. So the square root of Z squared plus A squared, quantity squared, times cosine theta. Z divided by the square root of Z squared plus A squared. I so can. Can you simplify it?
The bottom of the cube, right?
No, I could square that and take away the radical, but I also have 3 of them there, right? I have Z squared plus A squared times Z squared plus A squared to the 1/2 power. I don't think you're going to do any cross multiplying. But I don't know if you guys can see what I'm seeing. So an intermediate step. Is that okay? Here's my intermediate step. I'm going to, sorry to bore you. There's my intermediate step. I squared the square root. So now I can combine like terms. I don't know what this little dash is doing here, so let me get that away. There's no negative sign. So now I've got 2q1 q2 k times z divided by z squared plus a squared to the 3/2 power. I agree.
I'm confused where you got 3/2 power. You just,
Okay, I got this. Because you're not alone. None of this. After I wrote this down, none of this was physics. All of this was just geometry and algebra. But that's not necessarily easy, because your math teachers did not prepare you for this.
no, bro.
You were taught these things. They did not prepare you for this. We're not really done, but I'd like you to at least appreciate some things that are here. First, if you follow this all the way, great. If right now you're like, where's the nearest exit? I need to vomit. You've got another month and a half of this stuff being like this. But this is your first time seeing it. I would not expect everybody to think that this is going to be easy the first time they see something. I don't think you've ever seen anything like this before. I told you that, though, didn't I tell you? The beginning of this class is hard. This is the hard stuff. I am patient. I can wait. We have time. The worst thing you can do, though, is to sit back there stoically, nodding your head, but having no idea what's going on. The best thing you can do is say, Mr. Sheldon, I don't know where you got that. I'll be patient. We'll take our time. I'll give your brain a break once in a while, and we'll figure it out and make sure you get every little detail. Because I will blow through details if I think you're understanding them. And I'll be honest, this is a hell of a lot of stuff. So I said this is a Coulombs Law section. You understand that that is the least interesting part of all of this. Right? That just got us Q times K over R squared. Everything else here is what they're really testing. And there's something here. I don't know if you guys see it. Let's see if you see this. What happens to this force when z goes to 0? The force is 0. Does that make intuitive sense? If we go back to the problem, if z goes to 0, that puts the particle right here. Right? Won't that make the force go to 0? Because it's between the two particles. The math has to agree with reality, which is why an expression is more powerful. Because the expression tells us there's a place where the force will be 0. I can see it right in the expression. Now, you guys who are just in calculus right now, you guys doing those limit things?
We just finished those.
Aren't those fun? What's the limit as z becomes much bigger than a?
Does not.
Oh, it does.
Yes.
The limit as z becomes much bigger than a. Do you guys know how to do that? I know you just did limits in calc. So I'm just interested because I don't know if they teach limits like this. They do like limit as x goes to infinity for this function. They don't play around like this. So I want you to think about what happens under these circumstances, because you will be asked to do this on the exam. So maybe think it through a little bit. Where do you see a? Because it's asking you to make a comparison with z. So where do you see it? Do we all see that's in the denominator? In the denominator, I'm asking what happens to this portion of the problem when z becomes much bigger than a.
Oh, it gets,
Yes, sir.
It gets like really big.
It does get really big, but here's the real question. If z is much bigger than a in the denominator, would you agree that the denominator becomes dominated by z and a becomes unimportant? Like if z is 1,000,000 and a is 1, so that becomes 1,000,001? You understand why that's really no big difference? It's not really different than 1,000,000? So in a problem when you're asked to do this, set A to 0. That's what they're really telling you to do. That's the translation here. So in a case where you're told to make one variable much bigger when compared to another, set that other variable to 0. All right, so I made A 0, which left me with z squared to the 3/2 power. All right. I don't mean to punish you, but this is for the tangent yesterday. That's why I'm making you do this. So what is z squared to the 3/2 power? Z cubed. That's right. That's really not punishment. I'm just hoping you know that. Which means that this becomes z over z cubed.
How does it?
Go ahead.
I thought the number would get smaller, because if you're cubing your denominator, then the fraction gets smaller, right? When you say
The fraction's getting smaller, yes.
Okay.
We're not done yet, though. We're just going one more step further. Can I keep going, or do I need to back up? So you know that this is 1 over z squared, right? Here's where I make my point, I hope. So that makes this go 2q1 q2k over z squared. So if we get far enough away, stop it. If we get far enough away from the origin, the problem just becomes Coulombs Law. It's like the two charges are one charge. Right? There's a 2q right here, because it's like two charges, and then there's the other charge. So if we get far enough away, it's like the separation of those two charges doesn't matter. So this problem has something else in it. Something small, but I think incredibly interesting. And if you've been following me all the way to this point, then you might get this. If you haven't been following me to this point, you may not. So let's see if I have a few people who might be able to get this. When z goes to 0, we know our force goes to 0. When z goes to infinity, we know our force goes to 0. Do you see that? Both sides. So that means somewhere in the middle, the force becomes a maximum. You guys who had pre-calc know we can find maximums and minimums of functions, right? There's a place of maximum force. I don't know where it is, but I know that you have a method to find it. All right, look, regardless of what happens this weekend, we are doing the lab Monday. We're just going to stop everything and do the lab. Let's go. Start your homework. First 4 problems, you should be able to do all of them. We've done every one of those in class. And I'm glad you guys ask. If I had x times the square root of x, what would that be? Well, I can write this as x times x to the 1/2, right? X by itself is actually x to the 1 power.
Add them together.
So I add those together and I get x to the 1/2, 1 and 1/2 power, which is 3/2. So this is x to the 3/2. Does that make sense? You okay? Now, the difference is, instead of x, I had the parentheses of z squared plus a squared times the square root of z squared plus a squared. But it's the same thing, correct? Is that okay with everybody? I know I'm doing a lot. You understand that this isn't